And then when I'm in this state, now I will allow the pedestrian to walk, and then I go to EW to give it back because it needs to be given a turn after that. So take this as somebody else is understanding the problem and putting a design down. Don't try to force yourself to produce something identical to it. Just make something that is logical, that works. Okay, and you might add some assumptions, saying, well, you know what, I'm going to assume that a person can only cross when I have one traffic direction stop or something like that. You can put some conditions on your own and just make sure you are consistent with them. Do you have a question there? Is this fine? Do you have a question? Is that clear? Okay, so when you see X here, that means the system will operate as such regardless of the input. So whether P is equal to 1 or 0, doesn't matter, okay? You might, as I said, I warn you and I encourage you to think about the problem statement and come up with your own design. It's okay. And when I mark your design, I have told the TAs that I will mark the design question. It's not them for the final exam. The reason is that I want it to be flexible, that I see your process more than the final answer. That's what I need to see, that your procedure is logical, that you are able to put a problem statement and translate it into a state diagram. In a design exercise, what matters is your ability to come up with a state table or a state diagram. Okay? Because I will have other questions in the final that will test you on the other components, such as state reduction or diagram. Anyhow. So this is the state table. Once you have the state table, it's about producing these outputs as a function of the P and the state. We're talking about a mini machine, so which means when I produce these outputs, the one, for instance, here should be conditioned by something here on P, and that I am in this state. Okay? Take another example, another question. Design. My interest here is just to show you how you take a problem statement into a state diagram. That's what really matters here. The other steps are mechanical. You should be able to do them quite easily. Design a clocked, synchronous, state machine, finite state machine with two inputs, X and Y, okay? And one output Z. The output should be 1 if the inputs on X and Y since reset add up to a multiple of 4. You see? So that's the statement. So the machine has X and Y as inputs, and it looks at them and it says, are they a multiple of 4? Did I receive 4 ones, or 8 ones, or 12 ones that showed up in X and Y? It's almost like counting people coming through 2 doors, X and Y, and you are trying to find if what you have seen so far in the room here are multiples of 4. That's the basic idea behind this machine. So, put it in a very high-level language. Think about the machine and say, what happens if the machine has seen something like this? Just think about it in a high level, okay? I looked at the number of ones that showed up between X and Y, and I determined that there is 0 ones mode 4. That is, when I look at them, treat them as mode 4, I will have 0 there, which means I have seen either 0 or 4 or 8 and what have you. You see? You know when you take the modulus calculus, is that right?
Yeah.
Equation or function. You know how it works. Okay? So, I would consider this to be my state 0, which means if I am in that state, and now I start to think about the inputs. That's how you should think about the design. So if I am in that state, that means I either have seen 4 or 8 multiples. Okay, I have seen them before. So if I see 0, 0, then I stay in that state, because if I saw multiples of 4 and I see x and y to be 0, 0, that means things didn't change. So I stay there, okay? However, if I see now that x and y presented themselves as 0, 1, so that mode 4 violated, because I have seen another one coming in. So if I used to see 4 before, now I have 5. So where do I go in this case? If I see this, I go to state 1. So state 1, or S1, is a state that shows that I have multiples of 4 plus 1. Okay? If I see 1, 1, that means I was in state 0, multiples of 4, and 2 showed up. So that means I go to state 2. So what's state 2? State 2 says I have 2 mode 4, which is I could have 6, or I could have 10, or I could have 14, and so on. Is that clear? You see this? No? Or yes? You see it? You see, so 0, the remainder here is 0, the remainder here is 1, the remainder here is 2, the remainder here is 3, and that's about it, because after that there is no remainder. You get 1, you get to 0, or you get 2, you get to S1, and so on. So is that clear, how you can come up with a table like this? Clear? Okay, so when we are at S2, for instance, which means we have seen 4 plus 2 ones. So now, if we see 0, 1, we go to S3. What is S3? S3 is 3 plus multiples of 4, and we have it here. If I am in S3, that means I have 3 plus multiples of 4. So if I see 1, I go to S0 and celebrate. If I see S1, that means I got 1. That means I have 4. Okay, so now I see S1, so sorry, if I see 1, 1, that means I have 2. So therefore I have 3 plus 2 is 5. That takes me to S1, because S1 represents the fact that I have one mode, 1 left in a mode 4 operation. Is that clear? Clear? Is it clear? 50-50? Shall I go through this again? Yes.
One question. Were you on the, let's say you had 3 ones already, right?
3 ones?
Yeah,
all right.
You still have 1, 1, right?
3, okay. So we started at S0, because 0 mode 4 is 0.
No, I mean, let's say you're on the 4th state with mode 4, right?
You are at here?
Yeah.
So you have 3 now.
3 ones, right?
3 ones, okay.
Yeah, and now you still receive 1, 1.
1, 1.
So you go to state 1, right?
You go to state 1, that's right.
But you already have 4 ones.
Huh?
You have 4 ones and extra 1, so should you go to state 1, produce a 1 output, and then go to state 1?
No. What we are saying here, because if I have 3,
yeah.
Okay, so what does that mean? Means I have 1 more. Is that right?
Yeah.
So the number I have now is not multiple of 4.
Yeah.
So I don't declare I have a multiple of 4 yet.
Okay.
So that's why I will have to go to S1. If I produce Z equal to 1, that means I have confirmed that I have a multiple of 4. 5 is not a multiple of 4. That's what this machine does not look at 5 ones and say, I have 4 and 1.
Oh, okay.
It doesn't do it that way. That's a good question. Okay. So these are the states. I just have to go now and code them. Give them some stage coding. 0001 1110. Okay? From a design point of view. Now I go to implement my circuit. People ask me which flip-flop we use. It is up to you, really. Okay? Unless the question says use JK flip-flop or whatever. Okay? So in a design question, I will not force you to use any flip-flop. Okay? I will leave it up to you to use the flip-flop that you want. In other questions where I would like to test you on design components, I am going to ask you to use a specific flip-flop to achieve a certain design step. For instance, I would say, this is the state table. Determine the excitation equations if we are to use JK flip-flop. So you can see that. But in the design, I don't want to cripple you. I want you to be free. Do whatever you want, because I'm interested in your design sequence not on the final circuit. So you can use the flip-flop or JK flip-flop